All right, I know a lot of people have heard about saturated fats, and they may not have any idea what that means. And saturated refers to the individual fatty acids like palmitic acid and stearic acid. And in a saturated fatty acid, let's pick stearic acid. It has 18 carbons. Now the first carbon is an acid group, it's a carboxyl group. It's the other carbons that make it saturated. Every one of those carbons has 2 hydrogens associated with, except the end one, it has 3. It is saturated with all the hydrogens it can take. So that's a saturated fatty acid. Monounsaturated fatty acids, like oleic acid. Oleic acid has 18 carbons, but right in the middle of the molecule, it has a double bond. It's a cis configuration, and the only thing you want to remember about that is it puts a kink in the molecule and really reduces the melting point. So the melting point of stearic acid is about 160 degrees Fahrenheit. You've got to really cook that animal product to get it to melt. Oleic acid is like olive oil. The melting point is close to room temperature. So one double bond really reduces the melting point. Now trans fats are a whole different issue. Our cells don't make trans fats. We get trans fats either from hydrogenation of oils that they do chemically, and so they're trying to reduce trans fats in products. The reason that they hydrogenated fats chemically was to make it a solid at room temperature. They took corn oil and said, I'm going to make a stick of margarine out of this. Well, how do you make a stick of margarine out of an oil? So back when I was 11 or 12, Mom pulled butter off the counter and put margarine on the counter, and they were all bragging it was made of corn oil. And they said, look, you're eating polyunsaturated fat. Didn't mention the fact that they had to hydrogenate that fat, get rid of those double bonds so that it would actually be a solid at room temperature. So as long as you have saturated fats or trans fats, they have a much higher melting point and they'll be a solid. We do know that the trans fats behave more like saturated fats. They have a double bond, it's called a trans double bond. It doesn't put a kink in the molecule, so it doesn't reduce the melting point. And so if you take a stick of margarine that was just made of transvicenic, if you could get that much transvicenic, it would be a solid at room temperature. I don't know what it would taste like. I've never had any such thing. But trans fats have higher melting points. It's your cis double bond like you have in oleic acid and linoleic, linolenic. Those are going to lower the melting point. Polyunsaturates, I've talked a lot about oleic acid and monounsaturates. So they only have one double bond. Poly just means that it has more than one double bond. So linoleic acid, which is abundant in corn oil, soybean oil, safflower oil, that linoleic acid has 2 double bonds, which means it has an even lower melting point. You can take a bottle of corn oil and stick it in the freezer and it'll stay a liquid because those 2 double bonds, those little kinks in the molecule, really reduce the melting point. Alpha-linolenic acid has 3 double bonds. So it has an even lower melting point. And you'll get alpha-linolenic, some in soybean oil, primarily in canola oil, in our diets, normal diets. If you want to talk about something with really low melting points, the fish oils have 5 and 6 double bonds. So we go from monounsaturated with 1 all the way up to a fish oil that icosapentaenoic acid has 5 double bonds, docosahexaenoic acid has 6. You can't get those to freeze under normal conditions unless you keep liquid nitrogen at home. So those really lower the melting point, and they can only be made by some lower fishes and by the phytoplankton. So we're not very good at making those. Our cells can at tiny amounts, but we're not good at that. But the more double bonds you have in, the lower the melting point. And by the way, every time you add a double bond, you make that fatty acid more susceptible to oxidation. And so if you're cooking with something like canola oil that has alpha-linolenic acid in it, after a while you have to stop cooking with it because it starts picking up an off flavor. As you cook fish, everybody associates a certain smell with fish. And a large part of that smell is the oxidation of those long chain fatty acids with lots and lots of double bonds because they break down very easily. And the molecules they release, we detect as a fish smell. CLA is it's a conjugated linoleic acid. So you have linoleic acid, natural linoleic acid, has 2 double bonds. They're in cis configuration, so lowers the melting point. Conjugated linoleic acid has 2 double bonds, 18 carbons, 2 double bonds. But the double bonds are 1 carbon closer than they are in linoleic, so it's conjugated. And one of those double bonds is in trans configuration. So it's a trans fat, but so it has one trans double bond and one cis double bond. And so the most abundant CLA in animal products is cis-9 trans-11 CLA. There'll be a quiz later. But it has a cis-9 double bond, and that's what oleic acid has, right in the middle of the molecule. And so the melting point of cis-9 trans-11 CLA is very similar to the melting point of oleic acid because they both have that double bond right in the middle that's cis, that little kink in the molecule that lowers melting point. A small segment of the human population, about 5% of the people who are very diet sensitive, and that certain fatty acids, certain dietary components absolutely will increase their LDL cholesterol. And those fatty acids, based on animal studies, are the shorter chain fatty acids, myristic acid, which has 14 carbons, and palmitic acid, which has 16 carbons. Okay, well, my wife, Dana Smith, who's a Ph.D., R.D., L.D., all sorts of things after her title. She's a registered dietitian, licensed here in Texas. And my wife actually did a very nice study for her Ph.D. research in nutrition, where she compared the effects of shorter chain fatty acids and anything with 18 carbons or longer. And she used the pig as a model for humans, which for lipid metabolism, it's a great model. So she actually did a very nice study in pigs and fed these short chain fatty acids, saturated and unsaturated. So anything 16 carbons or less, and then 18 carbons or more. And those with 16 carbons or less increased LDL cholesterol in these pigs. Now, the pigs also saw an increase with the longer chain. They're not used to a lot of fat in the diet. But at least in this study, she got a much more profound increase in LDL cholesterol with a shorter chain. So in studies with rats and hamsters, basically they're looking at 14 carbon, 12 carbon, which is lauric acid, 14 carbon, myristic acid, and 16 carbon, palmitic acid. The evidence with the rodent species would indicate that these will increase LDL cholesterol. Anything with 18 carbons or more do not, but those fatty acids do not increase the LDL cholesterol. The other thing is that a lot of the times we make dietary recommendations for the entire population based on just a small percentage of the population. Yes, I do watch the fats that I eat, and for two reasons. One is I don't want my cholesterol too high. The other is I don't want to get fat. So, excess calories in, and it's hard to keep the fat off. So we really shouldn't be taking that small population like me and telling everybody that they should restrict their fat calories or dairy fat calories. And so that's one point. The other is, and this is a point that Ms. Teicholz makes in her book, there is really not a convincing argument that within a range of cholesterol levels up to about the total of about 260, that increasing total LDL cholesterol, or total cholesterol, I should say, really significantly influences your risk for cardiovascular disease. If you don't have other risk factors, if you don't smoke, if you don't have high blood pressure, and if you have a reasonable HDL level, at least well over 40 milligrams per deciliter, then the relationship between your total cholesterol and risk for cardiovascular disease is very low. So, two things: don't make recommendations based on just a small population, and is there really a risk within this reasonable level range that we see in humans? Is the association between total cholesterol and cardiovascular disease substantial enough to force these people to make huge changes in lifestyle and diet? Certainly, the recommendation to go to less animal foods and more plant-based foods hasn't helped, because for whatever reason, the American population has become, a much larger percentage of the population has become obese. And it's all happened to coincide with when we started cutting animal fats out of the diet.